When we think of an ice age, our minds often conjure images of vast, endless glaciers, woolly mammoths roaming a frozen landscape, and early humans huddled around fires for warmth. It seems like a distant, almost mythical past, a chapter of Earth's history long since closed. But the truth is rather surprising. We are in fact living in an ice age right now. Geologists call this period the Quaternary Ice Age, and it began roughly 2.6 million years ago. The defining feature of an ice age is not that the entire globe is frozen, but that permanent, year-round ice sheets exist at the poles. And if we look to Greenland and Antarctica today, we see immense blankets of ice, holding an astonishing 75% of our planet's fresh water. So, if we are in an ice age, why isn't London or New York buried under a mile of ice? Well, it's because an ice age is not a continuous, unbroken period of extreme cold. Instead, it's a long-term state characterized by cycles of freezing and thawing. The colder periods, when the great ice sheets expand dramatically, are called glacial periods. The warmer spells in between, like the one we're experiencing now, are known as interglacial periods. Our current warm phase, called the Holocene, began about 11,700 years ago, allowing human civilization to flourish in a relatively stable and mild climate. But it is just a temporary reprieve, a warm breath in a much longer, colder epoch. The very existence of the polar ice caps is the key indicator that Earth's thermostat is still set to a cool mode, geologically speaking. The end of the Quaternary Ice Age will only be marked when these colossal ice sheets melt completely, something that has not happened for millions of years. This perspective changes everything. It reframes our modern world not as the norm, but as a special temperate interval. We are living on a planet that has a natural tendency to cool down and cover itself in ice. Understanding this helps us appreciate the delicate balance of the climate we enjoy, and the powerful natural forces that have shaped and will continue to shape our world in profound ways. Our comfortable existence during this interglacial period can make it easy to forget the planet's underlying chilly disposition. The Holocene has provided the perfect conditions for agriculture to develop, cities to be built, and our population to grow. But it represents a mere flicker in geological time. The great ice sheets are still there, patiently waiting at the top and bottom of the world. They are a constant reminder that the Earth's climate system is dynamic, operating on timescales far grander than human lifetimes. The story of ice ages is the story of our planet's rhythm. A slow and powerful drumbeat of advancing and retreating ice that has dictated the course of life for eons. The current Quaternary Ice Age is not an isolated event, it's simply the latest chapter in a very long saga of planetary climate shifts. Looking back through the deep archives of Earth's history, scientists have identified at least 5 major ice ages that have gripped the planet over the last 2.4 billion years. The very first of these was so severe that it is believed to have plunged our world into a state known as Snowball Earth, where ice may have stretched from the poles all the way to the equator. These ancient cold snaps were transformative, each one profoundly altering the course of evolution and reshaping the very surface of the globe, carving mountains and creating vast lakes as they came and went. Each major ice age lasted for millions of years, and within them, the familiar pattern of glacial and interglacial periods played out time and again. The Pleistocene epoch, which is the first and longest part of our current Quaternary Ice Age, lasted for over 2.5 million years, ending only about 11,700 years ago with the dawn of our Holocene interglacial. During the Pleistocene, ice sheets advanced and retreated from the poles dozens of times. These were not small changes. At their peak, these glaciers covered up to a third of Earth's land surface, burying much of North America, Europe, and Asia under ice that was, in some places, several kilometers thick. The evidence for these past ice ages is etched into the landscape all around us. The Great Lakes of North America, for instance, are giant basins that were gouged out by the immense weight and grinding power of advancing glaciers. The fjords of Norway and New Zealand are deep, dramatic valleys carved by ice and later flooded by the sea. Even the rocks scattered across fields in places far from any mountains were often carried there by the slow, relentless crawl of an ancient ice sheet. These geological clues are like fingerprints left behind by the ice, allowing scientists to piece together the history of our planet's dramatic climate swings and understand the sheer scale of these past events. This long history teaches us that climate change is a fundamental part of the Earth's story. The planet has never been static. It has always been in a state of flux, swinging between hothouse conditions and deep freezes. The current quaternary period is simply our era's expression of this ongoing cycle. We are living within a grand, repeating pattern that is governed by forces far larger than ourselves. By studying these past cycles of freezing and thawing, we can begin to understand the mechanics behind them and, crucially, gain insight into what the future might hold for our planet and for us. The Earth has a memory, written in rock and ice, and it tells a tale of constant, powerful change. How does an ice age begin? Well, it's not a sudden event, like flipping a switch. Rather, it's a slow, gradual cooling process driven by the subtle rhythmic dance of our planet as it travels through space. These predictable long-term changes in Earth's movement are known as Milankovitch cycles, named after the Serbian scientist Milutin Milankovitch who first calculated their effects on our climate. These cycles are the primary pacemaker of the glacial and interglacial periods. They don't change the total amount of solar energy the Earth receives, but they do change where and when that energy arrives, especially in the northern hemisphere where large land masses allow vast ice sheets to form. There are three main components to these cycles. The first is called eccentricity, which describes the changing shape of Earth's orbit around the Sun. Over a period of about 100,000 to 400,000 years, our orbit shifts from being nearly circular to slightly more elliptical, or oval shape. When the orbit is more elliptical, the Earth's distance from the Sun varies more throughout the year, which can make seasons more extreme. This 100,000-year cycle has been found to match the timing of the major glacial periods over the last 800,000 years, acting as the main beat in the Ice Age rhythm. The second cycle is obliquity, which is the change in the tilt of Earth's axis. Over about 41,000 years, our planet's tilt wobbles back and forth between roughly 22.1 and 24.5 degrees. A greater tilt leads to more extreme seasons, hotter summers and colder winters. A smaller tilt, however, leads to milder seasons, cooler summers, and less frigid winters. Cooler summers are particularly important for starting an ice age. If summer temperatures in the northern latitudes are not warm enough to melt the previous winter's snow, the snow begins to accumulate year after year, compacting under its own weight to form the beginnings of a massive ice sheet. The final component is precession, which is the wobble of Earth's axis as it spins, much like a spinning top. This wobble happens on a cycle of about 20,000 to 26,000 years and determines which hemisphere is tilted toward the Sun during Earth's closest approach. When these three cycles align in a specific way, a more elliptical orbit, a smaller axial tilt, and a northern hemisphere summer that occurs when Earth is farthest from the Sun, they create the perfect conditions for a glacial period to begin. Less summer sunlight reaches the north, snow persists, and the great ice sheets begin their slow, unstoppable advance, reflecting more sunlight back into space and cooling the planet even further. The most recent glacial period, often what people simply call the Ice Age, reached its peak around 20,000 years ago. It was a world almost unrecognizable to us today. At its height, the average global temperature was about 6 degrees Celsius, or 11 degrees Fahrenheit. Cooler than our modern average. While that may not sound like a dramatic drop, its effect was profound. Immense ice sheets, thousands of meters thick, covered most of Canada, the northern United States, Scandinavia, and Britain. So much of the world's water was locked up in this ice that global sea levels were about 120 meters, or 400 feet, lower than they are today, exposing vast new areas of land, like the land bridge that once connected Asia and North America. This frozen world was home to an incredible array of giant animals known as megafauna. In North America, herds of woolly mammoths and mastodons navigated the icy plains, hunted by formidable predators like the saber-toothed cat, Smilodon, with its terrifying dagger-like canines. Giant ground sloths, some as large as modern elephants, ambled through the forests, while in Australia, a giant lizard called Megalania roamed the landscape. These creatures were superbly adapted to the cold, but as the Ice Age drew to a close and the climate warmed, many of them faced extinction, unable to cope with the changing environment and perhaps pressure from a new, highly adaptable predator. Humans. And humans were indeed there. Our own species, Homo sapiens, had been around for hundreds of thousands of years and had already spread across much of the globe. We were not alone, however. Other human species, like the Neanderthals in Europe and the Denisovans in Asia, also endured the harsh conditions of the glacial period. Yet, for reasons still debated by scientists, these other hominins vanished before the Ice Age ended, leaving only us. Recent discoveries like fossilized human footprints found in White Sands, New Mexico, prove that humans were present in North America at least 23,000 years ago, right in the heart of the last glacial maximum, a testament to our species' incredible resilience. How did our ancestors survive in such a hostile world? They did so through ingenuity and cooperation. They developed sophisticated tools including bone needles that allowed them to sew together fitted clothing from animal hides, providing crucial protection against the biting cold. They were skilled hunters who worked together to take down large prey. And their advanced social structures and communication skills allowed them to share knowledge and adapt to changing conditions. They lived in small, mobile groups, following the great herds and taking shelter in caves. Their survival through the last great freeze is a powerful story of human adaptability in the face of overwhelming environmental challenges. Given that we are in a warm interglacial period, the obvious question is, when will the next glacial period begin? According to the natural rhythm of the Milankovitch cycles, we are indeed moving towards conditions that favor the start of another freeze. The Earth's axial tilt, which is a key driver of the seasons, is slowly decreasing and is expected to reach its minimum point in about 10,000 years. This would naturally lead to cooler summers in the northern hemisphere, creating the ideal setup for snow to accumulate and for ice sheets to begin their slow march southwards. Based on these orbital mechanics alone, scientists predict that the next glacial period should, under natural circumstances, begin to take hold within the next few thousand years. However, the timing is not a simple calculation. Recent research, which has analyzed oxygen isotopes trapped in ancient marine fossils, has uncovered a more detailed pattern. Over the last 800,000 years, the great deglaciations, the ends of the major glacial periods, have occurred on a predictable 100,000-year cycle. This is linked to the combined influence of Earth's tilt and its wobble. The beginning of an ice age, however, seems to be triggered primarily by the tilt cycle alone. This suggests that the descent into a glacial period is a more gradual and perhaps less forcefully driven process than the relatively rapid warming that ends it. So, this means that our planet is slowly but surely heading towards the next phase of its climatic cycle. Without any other intervening factors, we would expect summer temperatures in the high northern latitudes to cool over the coming millennia. Snowfall would begin to outpace summer melt, and year by year, century by century, the ice would start to build. It would be an incredibly slow process, imperceptible on a human timescale, but inevitable on a geological one. The great natural clock of the solar system is ticking, and its hands are pointing towards a colder future for our planet. Of course, predicting the future is never straightforward, and there are other natural factors to consider. Solar activity, for instance, can fluctuate. Some scientists have pointed to the possibility of a coming period of significantly lower solar activity, which could trigger a mini ice age. This would not be a full-blown glacial period, but a regional cooling event, perhaps similar to the Little Ice Age that occurred from the 14th to the 19th centuries. During that time, temperatures in the northern hemisphere dropped enough for the River Thames in London to freeze over regularly. While not a global catastrophe, such an event would still have significant impacts on weather and agriculture. While the Earth's natural cycles are pointing towards a future cooling, there's a powerful new force at play, one that the planet has never experienced before: industrial human civilization. For the past 2 centuries, we've been conducting a vast, unplanned experiment with our planet's atmosphere. By burning fossil fuels like coal, oil, and gas on an enormous scale, we've released massive quantities of greenhouse gases, most notably carbon dioxide. These gases act like a blanket, trapping heat in the atmosphere and causing the planet's average temperature to rise. This human-induced warming is now overpowering the subtle, long-term cooling trend of the Milankovitch cycles. The amount of carbon dioxide we've pumped into the atmosphere is, honestly, staggering. For hundreds of thousands of years, as recorded in ice cores, carbon dioxide levels naturally fluctuated between about 180 parts per million during glacial periods and 280 parts per million during interglacial periods. Today, that concentration has soared to over 420 parts per million, and it's still climbing. We have in effect hit the accelerator on the planet's heating system at the very moment its natural cycles were preparing to gently apply the brakes. This interference is so significant that scientists now believe it could dramatically alter the Earth's climatic future. So, what does this mean for the next ice age? The consensus among climate scientists is that our greenhouse gas emissions have likely delayed its onset significantly. The extra warmth trapped by the carbon dioxide blanket will probably be enough to prevent the northern hemisphere from cooling sufficiently for ice sheets to form, even as the orbital cycles move into a favorable alignment. Some studies suggest that if we continue on our current trajectory, we could postpone the next glacial period by as much as 50,000 to 100,000 years. In essence, we may have inadvertently canceled the next ice age. Now, this might sound like good news, a lucky escape from a frozen future. However, it comes at a tremendous cost. The rapid warming we're causing is not a gentle, stable state. It's a violent disruption of the climate system that has nurtured our civilization. It leads to more extreme weather events, rising sea levels that threaten coastal cities, disruptions to agriculture, and the melting of the very ice sheets in Greenland and Antarctica that define our current ice age. We may have dodged the slow advance of the glaciers, but we've instead run headlong into the fast-moving dangers of an unnaturally warming world. Deep within the Atlantic Ocean lies a powerful and vital system of currents, a kind of planetary circulatory system that plays a crucial role in regulating our global climate. This system is known as the Atlantic Meridional Overturning Circulation, or AMOC. It functions like a giant conveyor belt carrying warm, salty water from the tropics northward near the surface, releasing enormous amounts of heat into the atmosphere and giving Western Europe its famously mild climate. As this water travels north, it cools and becomes denser. Near Greenland, this cold, dense, salty water sinks deep into the ocean and begins a slow journey back south, completing the circuit. This constant overturning of water is the engine of the current, and it's incredibly sensitive to changes in water temperature and salinity. For thousands of years, the AMOC has been a relatively stable feature of our climate system, moderating temperatures and distributing heat around the globe. However, scientists have discovered alarming evidence that this critical ocean current is weakening. In fact, studies show that it's now at its weakest point in at least 1,600 years. The primary culprit behind this slowdown is really the very thing that defines our modern climate crisis: global warming. The problem begins with the rapid melting of the Greenland ice sheet and other Arctic ice. As this ice melts, it pours vast quantities of cold, fresh water into the North Atlantic. This influx of fresh water dilutes the salty surface water, making it less dense. Because the engine of the AMOC relies on that surface water becoming dense enough to sink, this flood of fresh water is effectively clogging the mechanism. The water is no longer sinking as efficiently as it once did, and as a result, the entire conveyor belt is beginning to slow down. It's a classic example of a tipping point in the climate system. The potential for a complete collapse of the AMOC is a subject of intense scientific debate and concern. A startling study published in 2023 warned that, if greenhouse gas emissions continue at their current rate, a collapse could be much closer than previously thought. The study suggested there's a high probability that the AMOC could shut down sometime between 2025 and 2095, with a central estimate pointing towards the middle of this century. Such a collapse wouldn't be a gradual change. It would be an abrupt and catastrophic event, triggering rapid and chaotic climate shifts across the entire northern hemisphere and beyond within just a matter of decades. If the AMOC, the Great Ocean Conveyor Belt, were to shut down, the consequences would be nothing short of catastrophic. The most immediate and dramatic impact would be felt in Europe. Without the immense flow of heat being delivered by the warm surface currents, temperatures across the continent would plummet. Some models predict that average temperatures could drop by as much as 10 degrees Celsius or 18 degrees Fahrenheit in cities like London and Paris. In Scandinavia, the cooling could be even more extreme, with winter temperatures falling by a staggering 30 degrees Celsius, 54 degrees Fahrenheit. This would effectively plunge Europe and parts of North America into a localized, rapid-onset ice age, leading to much harsher winters and drastically altered seasons. But, the chaos wouldn't be confined to the North Atlantic. The collapse of such a major part of the global climate system would have far-reaching ripple effects. The tropical rain belts, including the vital monsoons that billions of people in Africa, South America, and Asia depend on for agriculture, would likely be shifted dramatically southward. This could lead to severe and prolonged droughts in some of the world's most populous regions, triggering widespread food and water crises. At the same time, the southern hemisphere would experience a general warming, potentially accelerating the melting of Antarctic ice and further disrupting global weather patterns. The Amazon rainforest could even begin to dry up, transforming from a lush carbon sink into a dry savanna. For the east coast of the United States, the effects would be twofold. While the region would experience some of the cooling felt across the North Atlantic, it would also face another, more immediate threat: rapid sea level rise. The northward flow of the AMOC currently pulls water away from the U.S. coastline. If that current stops, the water would surge back, causing sea levels along the eastern seaboard to rise by as much as a meter, over 3 feet, relatively quickly. This would inundate coastal cities, destroy infrastructure, and make storm surges from hurricanes far more destructive and deadly. This scenario, once the stuff of science fiction, is now being treated as a plausible and deeply concerning risk by the scientific community. An AMOC collapse would represent a rapid, non-linear shift in the climate system, pushing planetary conditions into a new and unpredictable state. It would be a change far faster and more chaotic than the slow grinding advance of a natural ice age. It really highlights the profound danger of pushing our climate system past its tipping points. We're tampering with the fundamental machinery of our planet, and the consequences of it breaking down could be severe, abrupt, and irreversible on human timescales. As we stand at this climatic crossroads, caught between the natural pull towards a future ice age and the unnatural push of human-induced warming, we can draw valuable lessons from our own past. Our Homo sapiens ancestors survived the last great glacial period, not because they were the strongest or the fastest, but because they were the most adaptable. They used their intelligence to create technology, like tailored clothing and advanced hunting tools. They used their social skills to form cooperative groups that could share resources and knowledge. They didn't try to fight the changing climate, they adapted to it, migrating across continents and finding new ways to thrive in a harsh and unforgiving world. This legacy of adaptability is really our greatest strength. Today, though, our challenge is different. We're not just responding to a natural change. We're the cause of a dangerously rapid one. But the same ingenuity that allowed our ancestors to stitch together hides with bone needles is now being applied to some of the world's most complex problems. Scientists and engineers are developing innovative solutions to reduce our carbon footprint, from renewable energy sources like solar and wind power to new ways of capturing carbon from the atmosphere. The same spirit of cooperation that helped small bands of hunters succeed is needed now on a global scale. In a fascinating echo of our past relationship with ice, there are now pioneering efforts aimed at actively restoring what we're losing. In the Canadian Arctic, a project is underway testing methods to refreeze sea ice. Using automated wind-powered machines, they pump seawater onto the surface of the existing ice during the frigid winter. This water freezes, thickening the ice layer by layer, in the hope of restoring some of the ancient multi-year ice that has been lost to warming. The ambition is to one day deploy hundreds of thousands of these machines to rebuild a vast area of the Arctic ice cap, a monumental effort to manually repair a part of the Earth's broken cooling system. The future of our climate remains deeply uncertain. We've pushed the Earth's systems far from the stable state that has defined the last 11,000 years. Whether our descendants will face a world of fire or a world of ice is, for the first time in planetary history, a question that depends partly on our actions today. By understanding the immense power of the natural cycles that have governed our planet for eons, and by recognizing the profound impact of our own activities, we can perhaps learn to navigate the path ahead with greater wisdom. The story of the Ice Ages is a humbling reminder of our place in the grand, unfolding drama of our living planet.